All right, we are group number 4, and we are covering chapter 7, which covers matrices, transformations, and vector spaces. Our group members are Joseph Rutenberg, Austin King, Kevin Tancho, Thomas X, Anya Hoke, Mustafa Yessi Yurt, Saif Wahid, Kenneth Halem, and Yusuf Kuf. All right. The matrix properties are as such. We have orthogonality, Hermitian, idempotent, symmetric, skew symmetric, similar matrices. I will go over some specific proofs found in Mosh's handout for Mathematics 2B at Dianza. Okay, so our first slide relates to matrices which are orthogonal and Hermitian, right? So a orthogonal matrix is a matrix in n dimensions that has a transpose, and this transpose is its inverse, right? So I have a matrix Q such that Q multiplied by Q transpose, or if you will, Q inverse, is the identity matrix that, right? 1, 0, 0, yada, yada, 0, 1. And you know the drill there, right? So that's pretty cool. You can just flip around the rows and the columns and you get the inverse, right? So I will cover Hermitian matrices right after we cover this proof, right? I'll go back there in a second. So a matrix is orthogonal if and only if its columns create an orthonormal basis. So we have a matrix A and a matrix A transpose. And so this makes sense because if you think of the vectors as column vectors, then you have matrices that are formed from these vectors. You multiply them, transpose, take them to columns, to vectors, to rows, then you get identities. And so this is all confusing when I say it in words, but you can see the math equations there written out. You have the magnitude of A being 1, which makes sense because it's an orthonormal basis, and otherwise its inner product with another matrix in this space is 0, being they are orthogonal, right? So this is the case for A, B, and C. The same goes for, so this is the case for A, showing that A is length 1, it's orthogonal to B, orthogonal to C. You can see how the same would be true for B and for C, right? So it is a somewhat incomplete proof, but these other steps are implied and somewhat unnecessary if you can follow what I did here, right? The concepts are just expanded. So, okay, I told you I'd go back to Hermitian, and I am. So a Hermitian matrix is a matrix, right? So it's conjugate transpose, a conjugate being a conjugate, transpose being transpose, right? Rows, columns, all switched up, and imaginary numbers negatized, right? The opposite's taken. So that conjugate transpose business is also known as dagger in the mathematics world. And so here I have expressed a Hermitian matrix in terms of a Pokemon move. So we have a wild complex matrix appears, right? We got the standard form e to the alpha, e to the imaginary I, beta, yada, 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 negative I, and we apply this dagger, right? We use a dagger. And the dagger is not very effective because M is a Hermitian matrix, so nothing changes. I thought that was pretty clever. So we got skew symmetric and just symmetric matrices, right? Pretty basic stuff, just definitions so that we don't have to redefine them explicitly each and every time we are talking about matrices, right? So it is as what you'd expect. The two look the same, right? We take the transpose, it's like they're mirror images of each other, right? The main diagonal is the same, and everything else just flip-flopped on the off diagonals and just reversed, right? It's like a mirror image across the main diagonal, and the matrix is equal to its transpose, right? Skew symmetric matrix is equal to its opposite transpose, so very similar to the symmetric matrix, except that it's negative when you take the transpose. And we have an example at the bottom, right, of a symmetric matrix and a skew symmetric. So I don't know if I can explain that anymore. If you don't understand it, then you just don't. Similar matrices. Now these are a little bit complicated because what they actually mean is not entirely clear at first. It is strictly defined as a relationship between two matrices such that when you multiply one matrix by a matrix P and its inverse, P to the negative 1, you get the similar matrix D, right? A and D are therefore similar. What this has to do is the diagonalization of matrices. So you have a matrix A, and you are able to get the eigenvalues with this operator. That's one example. There are others in which you have a similar translation, which is what a matrix represents, right? So I go into this step more thoroughly. You use matrix A eigenvalues to create eigenvectors. With these eigenvectors, you create a matrix P whose columns are the eigenvectors. This gives you P A P negative 1 equals D, right? D being the diagonalization, A being the matrix we want to diagonalize, P being the matrix formed by the eigenvectors in column form. If P is not invertible, then there is no diagonalization of A because P is a singular matrix. P being a singular matrix means that the eigenvectors do not span an area. They do not span an area. Therefore, our translation, when it is applied to a function or a space, a state, an eigenstate, it does it doesn't produce eigenvalues in the space of the matrix itself. This will make sense in later chapters, right? So let's see. Yeah. Okay. So invertible and idempotent matrices, right? A matrix is said to be invertible if there exists a matrix B such that AB equals I, B being the identity matrix, A being the original matrix. So here I have a augmented matrix. 1, 2, 3, 4, 1, 0, 0, 1. I move the numbers over, I make the numbers look different, and then I get the inverse. The steps for which are similar to row reduced echelon form. In fact, they are exactly the same because that's what it is. We take the left form, turn it into a 1, 0, 0, 1 matrix, which is the identity matrix, follow the same row operations throughout the entire augmented matrix, and with that we produce the inverse on the right side. And then idempotency is a strange one because if you have a matrix A which is idempotent, you will have that matrix multiplied by itself, resulting in itself. Gram-Schmidt process is a process which uses projections in n dimensions to create an orthogonal basis in the same vector space as a given non-orthogonal basis. So we have a vector space that is, say, not orthogonal. It's in a strange form, but it spans a specific space. We want to have a way to find that specific space, except we want to use a basis which is easier to notate, one that is orthogonal. So what that looks like is a process where we take the projection and we use the scalar produced by that projection and multiply that by our original basis to get something. Because if you take a scalar and you use that in combination with other vectors in that space as like a linear combination, you still get that same vector space but in a different form. So what we get with that is a orthogonal basis, which you can then turn into orthonormal if you so please. And this is an example. The steps are they're generalized here. This is just specifics and numbers. So I'm not going to go into too much detail there, but if you want, I can just glance at the details and how it looks like when you're actually dealing with vectors. That does it for that.